Okay, so welcome back to another video. So instead of just one functional equation, we are going to solve two different functional equations. We want to solve for f of x and g of x such that f of x times x1 plus x squared is equal to x squared minus 2 plus the definite integral from 0 to x of t times f of t dt. And then the second equation we have is 1 plus the definite integral from 1 to x of g of t dt is equal to the hyperbolic sine of 2x divided by 2 multiplied with g of x. So really no relation in between. We just find f of x that satisfies the first equation and then g of x for the second equation. Two separate functional equations we're working with. And strategies like solving for these, you usually want to plug in a simple constant to get some sort of value out of it. That's a good stepping stone. Then we just rearrange, some stuff around. So there's actually going to be involved some calculus, and with the integrals like this, we're actually going to be using some nice differential equations, specifically. Where actually one of them is going to be using a linear equation and the other one's going to be using a separable equation. Which do you think is going to be using? I'll let you figure that out for yourself. But don't want to give too much about it, but that's the whole takeaway of how we're going to be dealing with this. So why don't we actually just start with solving for f of x. So for this equation, let's actually start by plugging x is equal to 0. So that means 0 is going to be f of 0, then multiply with 1 plus 0 squared, set this equal to 0 squared, subtract 2, then plus the integral from 0 to 0 of t of f of t, and then dt. Okay, so with this, that means we notice that that's just going to be 0 because it's under the same, interval, 0 to 0. 0 over here, then 1 plus 0 is 1, so therefore we come to the conclusion that f of 0 is simply going to equal -2. So a good stepping stone for where we're going for, so let's actually just keep this in mind. So now the next step is, why don't we actually now take the derivative of both sides? So that means we have to apply the product rule over here. So what we have is going to be f prime of x, then multiply with 1 plus x squared. Then now take the derivative of 1 plus x squared, then times f of x. So that means that's going to be 2x, then times f of x. Set this equal to, so take the derivative over here. This is just going to be just 2x. -2, that's just a 0. And then taking the derivative of this integral, all you have to do is just apply the fundamental theorem of calculus. So put in the x over here for our integrand and then take the derivative. So that's just going to be simply just x times f of x. All right. So we notice that we can actually cancel out some stuff. We can actually subtract an x times f of x to both sides, and that will just leave us with just one quantity of that. So now this will just yield us with f prime of x, then times 1 plus x squared. Then we multiply, or not multiply, but add. So after the subtraction over here was just simply with just one quantity of x times f of x, simply it's just equal to just 2x. You might notice something, as mentioned, we're going to be using some differential equations. As you can tell, this is actually in a form of a first order linear equation. So what we can do here to make things a little bit simpler from here, why don't we actually suppose I let this over here, f of x, we'll let that equal y. So that will have to imply that over here, if you take that derivative, that's just going to be y prime. So now this will simply just yield us y prime times 1 plus x squared, then plus x times y, it looks a little weird, sorry about that, is equal to 2x. So now with this, in order for dealing with first order linear equations in a nice form that's such that we have y prime isolated by itself, you have to divide the 1 plus x squared into everything over here, and then that will just yield us with a nice similar form of the first order linear equation that you're used to when you're being taught in that. So after putting all this together, doing that division, so now we're just going to get that this is just going to be y prime, then add this with x divided by 1 plus x squared, then multiply by y, then set this equal to just 2x, all this being divided by 1 plus x squared. So we choose our function p of x and q of x of that form of the first order linear equation. As we can tell, we can see that p of x is simply just going to be x, then divided by 1 plus x squared. Our q of x is going to be equal to 2x divided by 1 plus x squared. So of course, when solving for first order linear equations, you want to multiply an integrating factor. So the nice form comes in the form of the function u of x, which I'll say that this is going to be equal to, so this is e, and then to the power the integral of your p of x function, so x divided by 1 plus x squared, and then dx. So of course you could solve this by of course applying the use substitution property. And so after applying all that, we're going to get that this is just equal to e to the power 1/2, then multiply with ln of 1 plus x squared, then simplify this even further that this is the same thing as e to the power ln of the square root of 1 plus x squared, then simplify it down so e and the ln cancel, so it's just simply just the square root of 1 plus x squared. Okay, so now with this we have to multiply our integrating factor mu of x into this entire equation over here from both sides. So that means I have the square root of 1 plus x squared then times y prime, and add this with x times the square root of 1 plus x squared, then divided by 1 plus x squared. That can be simplified, but we don't have to worry about that, honestly, because next step is afterwards, so 2x then times the square root of 1 plus x squared, then divided by 1 plus x squared. So now lastly, all we have to do is just take the integral of both sides, and you notice that this is actually doing the reversal of the product rule over here. So that means that's going to yield us with the derivative of, in respect to x, of the square root of 1 plus x squared, and then multiply with y, then dx. Then just integrate this side over here, so 2x. So simplify this down, we can get that this is 2x divided by the square root of 1 plus x squared, then dx. Okay, so this is actually just going to undo all this. This just yield us with just y times the square root of 1 plus x squared. And then we have on the right hand side, so this is actually pretty simple. Just apply the u sub, then that'll actually just cancel some stuff out, and then we get a simple antiderivative to solve for. That's just going to be 2 times the square root of 1 plus x squared. And then this is an indefinite integral, of course, that we're solving for, so make sure to add your plus c after that. So to get y by itself, simply just divide the square root of 1x to the square root of 1 plus x squared to both sides. So that means y is equal to just 2 and then plus c, then divided by the square root of 1 plus x squared. We're almost done because we have a constant we have to solve for. Remember earlier we had that f prime or f of 0 is equal to -2, so we can actually just plug this back in. So I can actually substitute this back to say f of x that we had for. So just plug in x is equal to 0, and then we can easily solve for our constant. F of 0, plug this in, so 2, well, let me put -2 first, and then set that equal to just 2 plus c divided by the square root of 1 plus 0 squared. Then if we solve all this out, we have that c is simply just going to equal -4, and therefore finally our f of x function that we solve for to satisfy the first equation is simply just going to be 2 minus 4 divided by the square root of 1 plus x squared. Okay, and so with that, that actually satisfies our first equation, the first functional equation that we want to solve for. So you can also double check and verify if you plug f of x back into here, you're going to get that the two things are going to equal to each other from plugging this substitution just like that. So with that out of the way, now let's actually move on to the second equation. Okay, so moving on to the second equation, essentially the work we're going to be doing for this is strikingly a little similar to what we just did from the first one, solving for f of x. So of course we want to find a constant, we'll choose a constant to plug in to make things a little bit easier to solve. So I think we can see that the easiest substitution for x we'll let that be is let x equals 1. As you'll notice that if I let x equals 1, so that means I have that, so this is 1 and plus the integral from 1 to 1 of g of t dt, then set this equal to just hyperbolic sign, so 2 times 1, which is just 2, divided by 2, and then times g of 1. Notice that we're on the same interval, so that's actually just going to get rid of itself and say that this is just going to equal 0. So I have 1 is equal to this. Then I'll just divide the hyperbolic sign of 2 divided by 2 to both sides, and we get that just g of 1 is simply just going to equal to 2 divided by the hyperbolic sign at 2. Okay, so we're just gonna keep this in mind. So do the same thing just like before. We're actually gonna take the derivative of both sides in respect to x over here. So what we have is that, so taking the derivatives, that means this is just gonna be 0. Over here, apply the fundamental theorem of calculus, so that means that just gets us with just g of x, and then set that equal to, so apply the derivative on the right-hand side. So as you'll notice that, of course, we have to apply the product rule. So what we have is, this is actually just gonna be, so the derivative of the hyperbolic sign of a function is the hyperbolic cosine, and then take that derivative of the inside. So it's just similar to like your sine is the derivative of sine is cosine in that similar fashion. So what we have is that this is just going to give us with the hyperbolic cosine of 2x, and then multiply with g of x. This is multiply the derivative. That means I have that this is 2 and then the 2's a cancel, so that's out of the way. Then now add this with, so this is just going to be hyperbolic sine of 2x and then divided by 2 and then multiply with g prime of x. Okay, so this may look a little bit complicated, such that we're dealing with in the name of the hyperbolic functions. So to make things a little bit easier, why don't we actually use the exponential definition of both these hyperbolic functions. So we know that the hyperbolic cosine of x, so let me actually just put that for example, is going to be in the form of e to the power x plus e to the negative x divided by 2, and then hyperbolic sine of x is just going to equal e to the x minus e to the negative x and then divided by 2. So with that definition, we can actually just fix some things up over here. So before we actually get to that, why don't we actually subtract the hyperbolic cosine of h of 2x to both sides, because it's associated with a g of x, and then I factor out the g of x, so now I have 1 subtract the hyperbolic cosine of 2x, then multiply with g of x, and then of course we just set this equal to just the right hand side over here, hyperbolic sine of 2x, and then divided by 2, multiply with g prime of x. So with that in mind, so now let's actually do the substitution for our exponential definitions into here. So 1 minus hyperbolic cosine of 2x, simply that's just the same thing written as 1 minus e to the power 2x plus e to the negative 2x and then divided by 2. Let's simplify this a little further because I have a 1 over here, so just get a common denominator 2, so it's a 2 divided by 2. Put that all together, and then you can actually defactor this out and write this as a square. So in other words, this is the same thing as written as negative e to the power x minus e to the negative x quantity square and then divided by 2. Okay, so now let's actually just get into this one. This one's a little bit easier. So I have the hyperbolic sine of 2x divided by 2. So what that gives us is this is just basically just e to the 2x minus e to the negative 2x and then divided by 4. Okay, so now let's actually put everything back together over here. And now another thing is, let's actually suppose that we let y equals g of x. And in standard notation, to make things a little easier, if I actually take the derivative of both sides, because we have a g prime of x, I'll write this in a dy dx, the Lyman-S's form. So what you're going to notice is that we actually have something of a nice differential equation. So putting this all together, so substituting back here, so I have now negative, then e x plus e to the negative x quantity squared divided by 2 times y. Set this equal to, so that means e to the 2x minus e to the negative 2x divided by 4, and then g prime of x, so that's why I can say that as dy dx. Doesn't this look very similar, right? So that's something in the form of a separable equation. So we can actually just solve everything by its own for dy and dx on its own. So let me actually switch to a different marker for this one. So doing all this together, if you get all the terms by itself, so dy and dx as mentioned, what we'll have is we have dy then divided by y, and then set this equal to now, for one, I have a constant, so I can actually just factor that out from the 4, so that means I just multiply 4 to both sides, so I have a negative 2, and then afterwards I have is e to the x minus e to the negative x, and then divided by e to the x plus e to the negative x and then dx. Then notice that with this the case, now let's actually integrate both sides of our integral or our differential over here. On the left hand side, of course, that's a very straightforward glance to see that that's just going to be ln of y. And on the right hand side, we just apply the u substitution, and then put this all back together. We have that now finding the antiderivative is going to be negative 2 to the times ln of just e to the x plus e to the negative x, and then now add this with c. Now, we can actually solve for y. That's a lot easier to do with, so just take the exponential base to both sides. So y is equal to just e to the negative 2 ln of e to the x plus e to the negative x and then plus c. Some things can be simplified out further since the e to the ln of x, or e to the power ln, then distribute the negative 2, so that's actually part of the exponent. So that actually goes on the bottom because it's a negative 2. And then we have a power c, so e to the power c when you separate this out with the addition. And then it's some arbitrary constant, so we can actually just give it a random letter if we choose to, what we're gonna do anyway. So what we have is I have y is equal to, we're gonna call this a, for a is equal to e to the power c, and then all this being divided by e to the power x plus e to the negative x and then quantity square. Okay, so now the last thing, of course, is we want to solve what that quantity, what that constant a is equal to. So of course we have that g of 1 is equal to 2 divided by the hyperbolic sine of 2. So we can actually do some simplification. So let's see, I have g of 1 equals 2 divided by the hyperbolic sine of 2. So we can actually fix this up and rewrite that. So hyperbolic sine of 2 would just plug this back in. So we have that, and if we multiply that together, of course, I have that this is 4 divided by e to the power 2 minus e to the negative 2. And then set this equal to a, and then divide it by, so it's just the same thing over here. We plug this at 1 too, remember. So that means I have e to the power 1 plus e to the negative 1, and then that's going to be quantity square. Okay, so now I'll actually just apply some cross multiplication over here. So a is then just equal to just 4 multiplied with e to the power 1 plus e to the negative 1 quantity square divided by e square, then subtract e to the negative square. You can actually apply the difference of squares formula, and what that'll do is that once that's decomposed, it's going to cancel out the term on one of the terms of the numerator. So now that just leaves us with 4 multiplied with e to the power 1 plus e to the negative 1 divided by e to the power 1 subtract e to the negative 1. And then by definition, this is actually going to be in the form of the definition of the hyperbolic tangent formula evaluated at 1, so that just yields us with 4 divided by the hyperbolic tangent evaluated at the constant 1. So that is actually our constant a is equal to. So now we just put this back together, so that means now g of x is going to equal to just 4 and then divided by e to the x plus e to the negative x square, and then multiply with the hyperbolic tangent at 1. So now we can simplify this even further. I'm going to write this over here. So g of x, therefore, this is by definition, this is actually the hyperbolic cotangent square. So that means I have that this is 1 divided by hyperbolic cotangent square of x, and then multiply with the inverse the hyperbolic tangent at 1. It's really hard to get, it's such a tongue twister. So with that out of the way, that's actually our formula, our g of x function that actually satisfies the following over here. And of course, as mentioned, you can actually plug this function back into over here to actually get the validation out of it. But indeed, this actually equals to each other once you plug this function in. So there we have it. F of x over here, let me actually box that. We have our f of x over here, and then our g of x over here. 2 functions satisfying these 2 different functional equations. So yeah, that's pretty cool if you ask me.